Okay, so I started out by defining what a relation is. That's any kind of association between two variables, or two numbers, I should say, two objects. And so the first one is considered, in this ordered pair, the first set is considered the domain, and the second number is, if you make that into a set, that's considered the range or the output values. And that you only list the elements of each, the domain and range, once. A function, the unique thing about a function is that it's a relation that assigns exactly one element in the range from any element in the domain. So whatever number you start out with, the input value, you get exactly one output value. Best way to think about this is price. Okay, this is the way I always associate it. Price is a function of an object. You can have only one price. You'd look at the cash register or the checkout clerk. Kind of funny if he or she gave you two prices for an item. It's one price, so that's a function. Okay, so that's the part that makes it unique. And so I went through a couple examples where obviously a one-to-one correspondence like this is a function, and this is. The second one is not a function because it assigns two different values in the range to the domain. And that you can have the same element in the range assigned from two different numbers in the domain. In this case, 0 and 4 both are assigned 1. That's still okay. It's still a function. It's like having the same price of two different items in a store. That works because any item has exactly one price. I went over function notation, f at x. So one of the reasons why I really like to emphasize having you define your variables is that you will also be defining your functions in this fashion too, so there's no ambiguity between having something where you're multiplying two variables, f and x, versus having a function f evaluated at a variable x. Okay. So you can say f of x or f at x, they're both used. And I gave you a couple examples here where we just basically dropped in values. We can drop in variables or expressions as well. And so we notice sometimes that if we enter a number, we get something that if we enter a number for the domain, an element in the domain, we don't get anything in the range. In other words, 1 divided by 0 is not a number, and so you don't have a number existing in the range, so you can't consider 1 to be in the domain of a function. Okay, so we exclude that. Now, the function itself can imply what the domain is. You basically, any legal operation basically says what the domain is, and sometimes when you end up with things like division by 0, you end up with operations that don't result in a number, and so this is what's meant by an implied domain. Contrast that with an explicit domain. For example, the domain of a price of an item in a store, or the function that assigns a price to an item in the store, the domain there is 0 to infinity, right? You would never expect a negative number to be priced. The store would not pay you to take an item away from the store. The store may have free items, and so that price would be 0, or it may have, any cost in there, depending on, if you go to a jewelry store, I suppose you can be in the millions of dollars, but that's an explicit domain because that's not, they're certainly able to label it with a negative number, but it's not part of the model. And so you contrast that with an implied domain here, where it's the algebra of the definition of the function itself that defines what the domain is. Okay, and so if you have something like that function that I showed you before, the domain is all real numbers that x does not equal 1. This is it in interval notation, and this is it in set builder notation. And so ultimately, set builder notation will be the most expedient way to define a function, because this business here of putting the braces, the x, and the such that are the same for every set, and then you just make a list of all your rules in there, where what x can equal and what it cannot equal. So this one may look a little bit more complicated at first than interval notation, but it is ultimately a little simpler. Okay, so two ways that we can find the domain is either saying, okay, what values does the denominator equal 0, and then you solve for x in that case, and here x minus 1 is not supposed to equal 0, so if we solve for x minus 1 equals 0, we find that x equals 1. So that then we make it x does not equal 1 because, well, we found the value that causes the 0, and the 0, of course, has to be omitted from the domain. When we have absolute value, or when we have square roots or something like that, the expression has to be greater than 0. And so just by saying that, you have an equation. X minus 1 has to be greater than 0. And then we solve for x, and we find that x has to be greater than 1. So you don't have to try any values in here. You basically set it to whatever rule you want, and then the solution of that will define the domain. And so in this case, in interval notation, this is 1 to infinity, including the 1, or in set builder notation, we can just say the set of x such that x is greater than or equal to 1. Okay, so did you find this already? Did we already go through that exercise? Okay, so you find that this is all real numbers except x cannot equal 3. Okay, so basically, there's three ways to define this. We can use the symbols. That funny-looking R is a way to say the set of real numbers, and so if all numbers work in there, or if all numbers are possible in the range, you can just state that R, you know, that the domain is the set of real numbers. You can make it an interval notation, and I've used set builder notation, and so here's a little bit of an explanation of how set builder notation works. Okay, try this one using set builder notation. I'm pretty sure we didn't get to this. Is that correct? Okay, so let's see. To get the domain of this function, you can't divide by 0. So this expression x times x plus 1 should not equal 0. So what values make it equal 0? Well, there's two values that make it 0, right? If x is 0, we have division by 0. And if x is negative 1, we have division by 0. So basically what we have is that the domain is going to be all real numbers except x equals 0 and x equals negative 1. So a way that we can write that then is just to write the set of x such that x does not equal 0 and x does not equal negative 1. Now, what we're saying is that what x is not supposed to equal, and for the purposes of this course, since we're only dealing with real numbers, we would just assume that x can be any other real number. Now, it's possible that we're dealing with complex numbers, although we won't deal with them in this course. And one of the ways that you can make it so x is part of the set of real numbers is that I could write that equivalently like this, where you say x, the set of x such that x does not equal 0, x does not equal negative 1, and then the way to state that it is a real number is that we can say x, and what this means is an element of, and then this, of course, means the set of real numbers. So I'm telling you right now, for this course, you don't ever have to put this, that x is an element of the set of real numbers. But if you just kind of looked at this, you think, gosh, this is a lot of math symbols and everything, but it really basically says that x is any real number except negative 1 and 0. Okay, that's the only thing that means, and that x is a real number as opposed to x can be a complex number or something of that sort. Okay, so there's an additional symbol for you in case you come across that in your reading or so. I'm not sure, I don't think our textbook uses it though. Okay, let's go to the movies. Not really, but let's use this as an example of a function. Okay, just, you would assume that the price of a movie is a function, right? Where you would go up to the window and you say, I want to buy a ticket. The person who's selling you the ticket will probably recognize that you're something over 14 but under 65, and they'll say, oh, that'll be 15 bucks. And there would be no surprises there, right? If you brought your little brother or little sister or your niece or nephew or something like that, and they were under 14, then you'd have to pay $5 for a ticket. And I'm not over 65, despite the rumors, but if I brought even my older brother isn't over that. But anyway, if I brought a friend who was over 65, that person would pay $10. And so it meets the definition of a function. Give your age, get a price, right? That's all there is. So now how do we define this mathematically? This is called a piecewise function. Because what happens is anytime that we're talking about our age, we're talking about what piece of the domain are we talking about. So your age is an element of the set that represents all possible ages. So we don't say 0 to 14 generally. It's understood that people are not under 0. And you would never presume what the ultimate age of a person is. I mean, you wouldn't expect somebody who's 110 to go see a movie, but it's possible. 120, there's probably nobody alive that's 120, but there may be an upper bound, but we generally don't say that. So what we're really doing here is we're dividing the set of real numbers into 3 intervals, right? And so we have a function that it's a constant, but it's a different constant depending on what part of the domain that you're speaking with. Okay, so we can notate this mathematically, and we call these a piecewise function. Basically, it's a function that has a definition for each part of its domain. So the domain of this thing is that if A is an age, the domain is the set of A such that A is greater than or equal to 0. That's a statement of the domain. But the parts of its domain are these things, right? Where you're either under 14, you're between 14 and 65, or you're over 65. So these together make up that domain, right? And so if C at A is the cost of admission, so there's how we're going to notate the function. C is the function of cost, A is what determines the cost. We'll notate the function as, here again, notice we use this brace, and it's not coincidental, it's intentional that this is the same thing that refers to a set, because we're looking at a set of definitions now. So the cost is 5 when A is less than 14, the cost is 15 when A is between 14 and 65, and the cost is 10 if it's under 65, if the age. So basically what you have is the value of the function defined here, could be an expression, and it would be kind of a silly pricing structure if 15 was A instead, but you can envision perhaps a movie theater charging your age up to age 14. So perhaps a 1-year-old pays $1, a 5-year-old pays $5, and a 10-year-old pays $10. That wouldn't be outrageous, I don't think it's common, but so this would be an A then. So you would, if you're under 14, you'd pay your age, and if you're between 14 and 65, you'd pay $15. So it goes up. So you can see how you can have different expressions here depending on what part of the domain that we're working on. So this is what's known as a piecewise function. Now, very often what you'll see is the word if. I'll just write if in here. That's common that you'll see this if statement, because then it more clearly says it's 15 if you're between 14 and 65. That's common. I think our book uses that notation sometimes. Sometimes it doesn't use it, but get used to not seeing it. The convention in math is that you put the piece of the domain to the right, and you put the actual definition of the function in its in the first position here. Okay, so this is the part of the domain, this is the value of the function. So in other words, these These three numbers are the three elements in the range. And of course, it can be an expression, not just a value. Okay, so let's look at the absolute value function. You know what that is. Basically, we notate that with two vertical lines on either side of the value. Like you can say the absolute value of x. We've done a few things, solved equalities and inequalities with that. We can define x as a piecewise function. Okay, so x has the opposite sign, or the value of the function has the opposite sign of x if x is less than 0. And x is just plain old x when it's 0 or more. Okay, so if we look at f at -2, which one corresponds to, this should say -2, -2. Well, the one that corresponds to it is that we say, okay, -2 is less than 0. So this first line is what corresponds to the value. And so our function is going to be the negative or the additive inverse of x. And so if you take negative x and x is -2, we have -2, which is +2. So we end up with a positive version of any negative number we put in, and positive numbers stay unchanged. Okay, everybody good with that? So don't mistake this negative x as having ultimately a negative value. It's the additive inverse of negative values, which is a positive value. Okay, so here's a function, a piecewise function that's perhaps a little bit more generic. Why don't you evaluate those three values? Okay, Lauren, what about this first one here? F at 0. What does f at 0 equal? 3. It equals 3. So how did you get to that?
I used 2x plus 3 and I plugged in.
You use the first one because 0 is less than 4, right?
Yeah.
Yeah, and so 2 times 0 is 0 plus 3 is 3. Okay? Everybody get that? You see, you decide which of these. Okay, so f at 7. What does f at 7 equal? Anybody? Yes?
17.
It equals 17, you said? So how did you, tell me how you got to that?
Well, like 2 times 7 is 14, 3 plus 3.
Okay, but this is the definition when x is less than 4, right? Here, x is 7, right? So you really want to use this one because x is greater than 4. And so you want to use this expression, so you have 7 minus 5. Okay, so f at 7 equals 2. All right, everybody follow that? Now what about the last one? What's f at 4? It's -1 because x equals 4, right? So it's important here when you're defining piecewise functions that they don't overlap. Like we can't say x is less than or equal to 4 and x is greater than or equal to 4 because then you end up with two values. Then you have to apply both rules to the function. It's okay if it doesn't if neither of them have the equality, what that would suggest then is that 4 is just not part of the domain. All right? Then you say, oh, 4 is undefined because it doesn't. But since we have the equality there, you put the 4 into the second expression, you get 4 minus 5 is negative 1. Okay, everybody good with that? Now, graphing piecewise functions always seems to be kind of a problem. So let's graph this piecewise function. And this is not going to be in the notes, but I think it's a useful exercise. You know how to graph 2x plus 3, and you know how to graph x minus 5. So let me grab a couple different colors here, and we'll look at this. Okay, so here's my x and y axes. If I were just to graph y equals 2x plus 3, what we would do is we would start at the 3 and we'd have a slope of 2. So we go over 1 and up 2. Here's 1 point. Over 1, up 2. There's the next point. I can go down and over, and I'd be here. So this would be my line. That's associated with this. Okay, so then the x minus 5, we have intercept of negative 5, and it has a slope of 1. If we put in, if x equals 5, y equals 0, so we're going to have a graph that looks like this. And so this here is going to be x minus 5. So for the piecewise function, I wonder if I have a green. I don't. Okay, so for the piecewise function, I'll define this in black. F at x equals 2x plus 3 if x equals, or if x is less than 4, and x minus 5 if x is greater than or equal to 4. Right here the value changes, right? So if x is greater than 4, this point on, and this is no longer this, this represents the second line, and the first line is only there if it's less than 4. So if we take, 4, I guess it didn't go up. And this would be up here like this. So what we essentially have are two lines. One that goes up to but not including, this point here is going to be 11, or it's going to be 4, 11. That's not included here, but when we're at 4 it starts here. So you need to just graph the piece of the piece of the function that represents whatever domain we're dealing with. So in this case, this line looks like x minus 5, but we only draw it from 4 on. So one of the ways that you can make piecewise graphs is just what I did. Draw the whole function and then erase the parts that aren't pertinent to the domain. So here I had x minus 5, but it's only if x is greater than or equal to 4, so all this business here I erased. Same thing here, I didn't have much to erase, I had to extend this up here, but 2x plus 3 is this line, but it only goes up to this point, and it doesn't include that point. Okay, so, that's basically how you graph it, where you just take the individual segments. Now, if I were to graph the other function, the one that had to do with movie admissions. And here I'll make my scale where this is 14 and this is 65. You would pay, what was it, $10? Is that what I had? Let me go back to it. Yeah, you'd pay $5 if you were under 14, but not including 14. So you'd expect your graph to look like this. And then between 14 and 65, including both of those values, the price is at 15. So we put a dot on each of those. And then if you're over 65, it's $10. So it's not, doesn't include 65, but everything over it. And so that's the way you would notate that particular graph. Okay, so each piece is graphed individually. And we could do the same thing here. We can graph x equals 5, x equals 10, or c in this case. C equals 5, 10, or 15. And then just erase the parts that it doesn't pertain to. Like 10 and 15 have nothing to do with 0 to 14, so we would erase those. Between 14 and 65, we'd erase both of these because it doesn't pertain. So anyway, you'll have a couple of those in your homework to sketch out. Okay? Yes?
For the point that you have there, 411, how did you get 11 after 1?
Well, I just put it in my head. I said, how far does it go up to? And if I put a 4 in here, I get 2 times 4 plus 3. So that's how I got to 11. Now, I know it doesn't equal that, but if it was, let's say, 3.99999, it'd be like, 10.99999. Okay, so I computed the endpoint, but I didn't include that. All right, everybody good with this? Okay, so that's chapter 3, section 6. What I want to do now, so let's say we have this 2x plus 1. I can make individual points, and I just basically can plot them. Here I plotted it on this graph. If I have the absolute value of x, I can do the same thing. I can make points, and then sketch out my points and connect the dots, or a piecewise function. Basically what I did was I calculated the points, and then I plotted them. What you have to be careful for is where it changes in value, and so here is where the change in value is. So here I pay particular attention to, does it start there or does it end there? What's open circle and what's closed circle? And here you can see when x is greater than 0, that's where the, or when x is greater than or equal to 0, that's the closed dot. This one, the strict inequality, has the open dot, so I can graph like that. I assume you can do all that, right? You've done a certain amount of that already. Okay, what I want to do now is just go over some basic functions. When you take Math 13, the pre-calculus textbook calls these functions toolkit functions. And the reason why they're called toolkit functions is because they're basic functions that you can make other functions out of by combining them in various ways. But these functions are simple enough where you should always be able to keep what the general shape is and what the location of these graphs are just from memory. So when you have a constant f of x equals 3, that's a straight line. The square root is half a parabola turned on its side, right? The square root always gives you a positive number, and it only includes positive numbers. So at 1, 1, that's 1 point, but as x increases, f at x increases, but not quite as fast as x. If we just have f at x equals x, that's just a straight line going through the origin with a slope of 1. A parabola, I think you know what this one looks like. It's just a curve like this that is more curved towards the vertex than on the sides, and it includes the points 1, 1, 1, and negative 1, 1. The absolute value of x looks just like x, when it's beyond, when x is positive, when x is negative, it actually goes in the other direction. And then the last one would be f at x equals x cubed. And so this one starts in the lower left and goes to the upper right, and it's kind of curved like a parabola. It's curved a little bit more broadly, but these two functions are useful to remember because this one only yields even numbers, and this one can yield odd numbers when x is odd. So, for example, the cube root of -2 or the cube of -2. So -2 to the third power is going to be -8. So it retains its sign as you use that. Okay, so we have some ways when we have graphs to determine is something a function or is it not. And so probably the most useful tool that we have is the vertical line test. And so what the vertical line test is if you imagine a vertical line taking any value of x, it should only cross the function once, right? Because for any value x, this is what the function equals. And if you took the vertical line test on this particular one, this value of x corresponds to two values in y. So this is not a function. So you think of the vertical line test as a way to decide, if you only have a graph, if you have a function or not. Okay, so this first one passes it because no matter where we move it, it only goes through one value. This one fails it because it, in many places, goes through the curve twice. So the second one is not a function. Okay, so let me go through a couple graphs here. And these are related graphs. Here's my toolkit function, absolute value of x. Now I want to, let's say, make a variation of that, where I'm going to first subtract 2 from x and then take the absolute value. And then on the other one, I'm going to just take the absolute value of x and then I'm going to add 2. Okay, so if I make it my graphs, I can make my values here for f, g, and x just by plugging in numbers. And so here's my toolkit function. Now I know I'm going really fast. Don't worry about copying all the values down on the table. You know, you can, if you really want your notes to be complete, they'll be posted so you can fill in those numbers. But I'd really like you to more conceptually see what happens here. When we graph g at x minus 2, notice when x is, let's take a positive number, if we say, if x is 1, f at x is 1, and then 1 minus a -2 makes a -1, absolute value of that is 1. So this value remains unchanged. But almost every other number, like if we take 4, we take 4 minus 2, and so we have the absolute value of 2. When we plot all those, you see what happens here. We have exactly the same shape of the graph, but it's moved over 2, and it's moved to the right. So there's nothing special about 2. If I put in any other number in here, we would expect that it would move over 3 or 4 or 1 or whatever. If this number is positive, so I have x plus 2, this thing moves over this way. So one of the things that we can think about in these rules, that if we have, and this is true for all the toolkit functions, for any function in fact, that if before we evaluate the function, if we just add or subtract a number to x, we're going to move the function back and forth. Another way to think about it is that we're not changing the function as much as we're just changing the axis of the graph, right? Because when we consistently add or subtract something from x, it's like moving the scale over. Okay, so this is what happens when we have x minus 2. Now if we put the plus 2 on the outside, what we get is this here, where we just take every value that we have for absolute value of x and add 2 to it. So when we add something outside of the function, we're just moving it up and down. Okay, so I'll let you catch up while I'm erasing the rest of the board on your notes here. Okay, everybody good here? You're up with me enough? Great. Okay, so here's the generalization. If we're going to take a function and add a constant to it, we're going to move it up by c units. Or if we subtract a value c, and we're assuming c has a positive number now, then we're going to actually go down. So we would, so just like with that toolkit function that I added 2 to the absolute value, it moved it up. I can move it up or down. If I add or subtract, now c of course here is positive. When you see x minus a number, it's going to move it right. And when you see x plus a number, it's going to move it left. So this one works the way you would just expect, right? You add 2, it goes up 2. Changing the direction of this thing takes a little bit of thought. Don't mistake this x plus c as moving, that you're increasing x, and in fact, what you're doing is you're moving the scale back. And so this one moves it to the left, this one moves it to the right, just like we saw with the x minus 2, how the absolute value function moved to the right. Okay, so that one works opposite of what you would maybe guess without giving it much thought. Okay, so if we take another toolkit function, here's x squared. Let's say I wanted to do this to it, f at x minus 3 plus 2. We're going to expect that h at x is going to move over 3 this way, and then it'll move up 2, and so ultimately our graph will look like this. Now if we make the substitution in our function, now notice it's not only this point, the vertex, that moves. That's an easy one to move if you need to make a sketch, but every other point on the curve moves in exactly the same fashion. Right 3, up 2. Okay, so what I didn't write here was what the ultimate function is. So if f at x equals x squared, then f at x minus 3 plus 2, that's a really lousy 2, equals x minus 3 squared plus 2. Okay, so there's the function that is represented by the red line here. Now, of course, we can expand this if we want to and say this is x squared minus 6x plus 9 plus 2, which then equals x squared minus 6x plus 11. So here, if I ask you what does this look like on a graph, you could probably guess, well, it's a parabola, and you certainly wouldn't mistake it for just plain old x squared. But this is harder to imagine what's happening than in a form like this, where you have a definite, I'm modifying x, and then I'm modifying my function on the outside. So at some point in this course, probably about 2/3 of the way through the course, so maybe weeks 10 or something like that, we'll go over how do we transform this into this form so we know how the function behaves. And it's called completing the square when you do that. Okay, so let's talk about reflections now. Now, by reflections, I don't mean self-meditation or anything like that. I mean reflections as reflection in a mirror. Let's take our square root toolkit function. And what if I put this, a negative in front of this x? Now, the domain of f at x, of course, is going to be 0 to all positive numbers, right? We can put a 10 in here and we get a real number. This one, if we put a 10 in here, we'll get square root of negative 10, which is an imaginary number. That's not what we're interested in. But if I put in a negative 10, then I get the square root of 10. So this thing, the domain changes. Remember, this had a limited domain. It's only for positive numbers. The domain here has changed. Now, if I put a negative on the outside, what happens is whatever I get here, I'm going to take the negative version of it. So remember, the range also was in the first quadrant. So just from an expectation standpoint, this thing will reflect it about the y-axis, and this one will reflect it about the x-axis, and I'll show you that now. So if we were to take a bunch of numbers that are easy to take the square root of, -9, -4, 1, okay, we don't get numbers here, so x is not in the domain of f for when x is less than 0, but we can compute it when x is greater than 0. We have just the opposite, g at x, so if negative 9 is 9, so we can take the square root of that. Negative 4 is 2, so we can take the square root of that, and so on. Once we get into positive numbers and make them negative with this negative sign, it's outside of the domain, so we have no values. And with h at k, it's just exactly the same as f at x, or excuse me, h at x. It's exactly f at x, but with a negative sign in front of it. Okay, so there's our f at x from our toolkit function. So there's g at x. Notice it looks the same. It's reflected about this x-axis, so it's like taking this and turning it over. But the domain is different because we've changed that limited domain into something else. So it's reflected about the y-axis. And then h at x, when we take a negative in front, we're flipping it this way. We're flipping it about the x-axis. Okay, so the generalized thing is that if you take g at x equals f at negative x, we're flipping it around the y-axis. So change the variable sign, and it goes about the x-axis. If we change the function sign, we reflect it about the x-axis. Okay. This goes back a couple slides now. What does this do now? If I have g at x equals x plus 4 squared minus 5, how does that compare to x squared? So if you can draw a real quick diagram of what x squared looks like, what would you expect g at x to look like, just based on that? What do you think? So this differs from our toolkit function in the sense that in parentheses here we've added 4, and then outside of the function we've subtracted 5. Yes?
It'd probably be to the right 4 and down 5.
To the right 4 or to the left 4, right? Because remember, plus is left,
Okay, yeah,
and
to the
then
left.
minus is right. So you're mostly right, except this goes 5
Left.
units to the left, 5 units down, 4 units left, sorry. So instead of this, it's going to move 1, 2, 3, 4. It's going to move here and then down 5. 1, 2, 3, 4, 5. So there's our new vertex, and this thing is going to look like that. Okay? So let's put this in words. Part of this course is not only to do the computations and make graphs and things like that, is you might even get this on a test or a quiz or whatever, and it says describe what this is compared to the function f at x. You would just say here that g at x is the same at f at x, moved over to the left 5 and down, or to the left 4 units and down 5 units. Okay, so be able to make that into a sentence to be able to describe it. That's part of the goal of this course, is for you to communicate that. Okay, here's one. What if we want to sketch this graph? Now, I don't have any explicit equations here, but I do have some points. So how would you do this? My k at x is going to be h at x plus 1 minus 3. I don't have a formula. But see if you can first envision what it does, and then see if you can actually make the plot of it. I'll give you a moment to think about it, put it in your notes. I will give you the answer, but I'd like it first to put in words what happens, and then see if you can't make a graph of how this is going to look. Okay, so who wants to give me the words on what works here? What does this do? Describe it verbally. Anybody? Yes?
It's a horizontal shift to the left, 1, and then vertical shift down, 3.
3, okay. So when you make a graph, how would you do this? Well, you know what it's going to do. So you can take any particular point and you can move it, right? Okay, so the way we'll do that is we subtract 1 because it's going to move it to the left 1, right? And then we're going to move it down 3, so we're going to subtract 3. So the tricky part here is to recognize which direction you're going to go. Perhaps 1 is the easiest one to start with. If we're at 1 and we're going to move it left 1, that becomes 0. And 3, if we're going to move it down 3, that's going to be 3 minus 3 is 0. So there's our ordered pair for k at x. And if I make a graph of that, I plot those 4 points, and I know that I can connect those points because nothing really changes linearly. It just goes left 1 and down 3, and so there's our graph. So let me ask one more question now about domain and range, about understanding transformations. Let's take something similar to this, and let's say I have g at x equals f at x minus 3 plus 2, okay? Now, I'm going to say that f has a limited domain, okay? And I'm going to say f at 5 equals 7. So I know that this is in the domain and the range. I don't know anything else about the function. What is exactly one point that has to be in the domain and range of g? See what I'm asking? I have a point. I'm not telling you what the function is. I'm telling you how the functions relate. But if this is part of f, both in domain and range, what has to be a point in the domain and range of g? Yes.
Is it 8? 8 minus 3 would be 5 plus 2 is 7. So.
Okay, so we have g at 8, right? Because if we do 8 minus 3 is 5, and so we know we can compute it. So what does g at 8 equal? 7?
Yeah.
How about something else? Because that's what f at 5 equals. We're doing g at 8. So if we put an 8 in here, we get f at 5, which is 7, and we still have to add 2 to it, and so we get 9. Okay, do you get that? This is kind of an abstract notion about, what happens, when you have one point that you know in a domain, and you have a definition relating to different functions. It must exist in the other. This point, 8 comma 9, must exist in the domain and range of G. Okay? Good thinking. Good thinking about making this an 8 because we want this expression to evaluate into 5. And then we have this expression here then that evaluates into 7. Right. That's all I got for today. So I hope your Monday goes well. Everybody sign in. Okay, see you on Wednesday.
Thank you.
I had a quick question.
Yeah.
For on the homework on 47. when it's for fractions, you said to multiply by the common denominator.
Mhm.
So it'd just be, we multiply by 4 and multiply by 3, and there's both equal to 4.
Yeah, kind of. Okay, so we have x over 4 plus y over 3, and what was the rest?
It's less than or equal to 1.
Less than or equal to 1. Oh yeah, if you have homework to turn in, please put it up front.
Oh, you,
Okay, so what you would do is you would multiply both sides by the common denominator, which is 12, which is 4 times 3. So 4 times 3, x over 4 gives you 3x. And then 4 times 3 times y over 3, 3's cancel and you get 4y. And that's going to be less than 12.
okay.
Okay, you see how I did that?
Yeah.
You're multiplying both sides by 12. And then it happens to clear this fraction because what you get here when you distribute this is 4 times 3, and this is 4 times 3, okay? From distributing it, the 4's cancel and you get 3x, and then the 3's cancel and you get.
Okay. Alright. Oh,
Okay.
yeah. And then, do you have staples? Or should I just put
I
my,
don't, you need to have the staple though.
Can I just put my name on both?
Yeah, okay, for now, but make sure it gets stapled, okay?
Okay.
And don't give me a ragged edge.
Yeah.